Right. Hello, everyone. I am Professor Caudill, and we have barely made it through Chapter 3, Through the Abyss. I think we got a lot out of it. Um, those final questions were pretty tough. So, what do we learn? It's one thing, like I can make a function for all the variables. It's like, hard part is extracting the knowns from the question. It's even harder when the question deliberately obfuscates the knowns. And yeah, I wish it was that simple where you just convert English into variables, put the variables in a function, like answers the question. I wish it was that easy, but um, it gets hard when you have let's say they give you an unknown. So let's say U is a list of unknowns, unknown one, unknown two, or variables. Doesn't matter. So we have a function that maps these U's into, let's say, P. P answers the question. It gets tougher when you get like composite functions equals P, where some elements of U are not not known. Some elements of U are not known. Are not known. So if we yeah, and you have to convert an English of your variables. You have to convert that to English to variables. That's also a tough. It's not always easy, especially when it's a combination of hidden variables. Did like the question deliberately hides variables, and when it's like a composite function. So what is a composite? So you take like f of u, okay, that is p, and then p gets put into a function that gives you q. So it's easy to do this. It gets tricky to do this when you have to kind of see it in different steps. And yeah. All right, so we can just kind of take a breather. Have any water? I don't think so. I think I can make it. So we can just kind of take a breather and really soak in what chapter 4 has to offer. So it's going to be pretty similar to chapter 3, just, obviously in two or three dimensions. So we got a picture of, airplanes, one example. So what is this chapter going to be teaching us? Hopefully displacement and velocity vectors, acceleration vector, projectile motion. So that's going to be everything here is parabolas, pretty much. Uniform circular motion. So two words come to mind: centrifugal and centripetal. I know one of those terms, things tend to one of those terms is like a black hole, and the other term is like explosion where things are flying away from the center. And then relative motion. So, all right. So I know you guys can read, so I'll try to read silently and pick out, what stands out to me. So, curve pass. If you really want to be specific, everything's kind of curved. Um, yes and no. If you break down time into like Planck's time might be discrete, but it makes estimates easier when everything's curved because then you can do calculus, take everything in the limit. Um, so this may or may not be true. Definitely, if you're doing calculations, curve fitting. So if you have a bunch of data, obviously this is discrete. This is like a zigzag. So this is your this is your position function. You can estimate the velocity by curve fitting, and that you can use like linear algebra techniques, but basically your one method is you take every point. It's like the square root of all the sums of something. I don't know off the top of my head, but you basically take a curve and you map it to this data. Okay, so now you have some function via t, and then you can take that lets you take calculus of your this a, which is another way of saying that is you're taking the limit calculus stuff. Don't have it totally committed to memory, but I know it's like b t plus delta x. Add or subtract? Maybe it's add. And then it's divided by delta t. Don't quote me on it, but it's something like that. It's like taking the average, but taking infinite averages. Okay, so treatment motion is giving us a foundation. Okay. So we assign each jet a unique position vector. Assign each jet. So this language sounds like function. So if you have some function, what you're really doing is you're taking a set, say A1, A2, P. So you're taking each element here gets assigned to another one. So if this was jets, jet A gets a vector. Jet 2 gets a position vector. It's in its unique. Jet A and Jet 2 cannot have the same position vector unless they're somehow one's inside the other. So we're going to use the same basic displacement. We're going to use the same basic equations, so that's nice. So there's two types, projectile. So projectile, everything projectile is parabolas because gravity, um, you know, the Earth, you got the force of gravity coming down. So everything is getting attracted to the center point. So when you throw an object, not only is the Earth spinning, but when you throw the object up, it's getting forced down. So there's also like, you know, the Earth is spinning, and then there's also the force of gravity. So there's several things, but I would say these are kind of negligible for the most part. Um, and then centripetal force, I think that's when things tend to gravitate towards the center. Uh, so centrifugal. Don't quote me on these. I'm using the term exactly right, but that's like when something spins outside of, goes away from the center. So that's two types of motion. What this chapter is going to cover. Each jet, its relative motion. So I think Einstein relativity showed that relative motion depends on the frame of reference. It's good videos on World Science Festival YouTube channel. And on that, I like Brian Greene's daily equations. Those can be pretty informative videos. So I guess we're getting into section 1, displacement and velocity vectors. So there's position vectors. So I didn't originally, but now I prefer S of t for position vector. Um, so S of t, your position vector might be something like that, where this is time and this is distance. Okay, so I'm sorry. So like at 10 seconds, he might have ran 100 meters. So going, when this slopes down, that means he's going in the opposite direction. And then your velocity t is going to be how fast this is changing. So if you're rising, it means you're picking up speed. It's going to be pretty similar. You decrease speed. So I don't have like the best intuition for like graphing these, but I know um, it's a good skill to have. I wish I was better at it. That's why we, you know, get better as you do it, basically. So displacement and velocity. So they're straightforward extensions. So that's a relief. So we have different rules. We have to follow vector algebra instead of scalar algebra. Okay, so we're going to use R3 space basically the XYZ coordinate system. Generally use coordinates X, Y, and Z. A particle at a point XYZ. Okay, so it's moving, and it's this. So the motion of a particle so when it says particle, that's like anything with matter. Uh, anything smaller than a particle, I don't think it can hold energy. So, and I think classical physics breaks down if you go smaller than a particle. So this is like the edge of where this is as far as you can get with like Newtonian, whatever, Newtonian and Einstein physics. So motion is described as a point with a set of functions position vector. Okay, so they're calling this R T. So I know it's kind of redundant to be rewriting it, but it's helpful for me, and it's probably helpful for you just to get like the motor uh, practice, because sometimes when you rewrite it, you find your own kind of way. Um, Mathematicians love shortcuts, and rewriting it and manipulating it is one way to kind of make your life easier and more personalized. I think the best way to learn anything is to make it so personalized that it doesn't make sense to anybody else, but it makes sense to you. Um, and then when you're teaching, it's like you're converting your nonsense into something sensible. So don't shy away from nonsense if you're learning, basically, because what's nonsense to someone else might make a lot of sense to you. So you find your own way. Like you could um, like obviously this could be expressed as a dot product. I think I showed last video how to do a dot product with this. So yeah, so I'm not in a rush, so we can just do it. So for motion in 3 dimensions, the textbook says vector R of t is k, where j, k are unit vectors. Show me how to express this with matrices or not. So if you remember from our like chapter 2 vectors, dot products were a big thing. Dot products are basically the sum. Try again. I don't Not a huge fan of that. Maybe it can generate something um, better. So see, uh, try again, but can you make a matrix? Okay, so yeah, so this is kind of like this is what I like, except this is not defined. This should be on the other side. I think your ordering is wrong. Should swap these. And I broke it. I want this matrix on the left side. Okay. So R of t is I dot R of t. So R of n, and this is I of n. So if, in a way, you could say you can take this into 4 dimensions. If you think about it like this. So you have, so this should be a matrix. Um, okay. Maybe it would be a matrix. Let me rewrite it. So maybe R of t is a matrix of unit vectors. I'd rather change this to U. Is some amount of unit vectors. This is a matrix. And then n-dimensional space times t. That gives a vector function. So again, that might be completely nonsense. It might actual mathematicians might be laughing. Looking at it different ways, there's no way you can go wrong. Well, it's better to have 10 perspectives and all 9 of them being incorrect than to have one perspective and that be the right perspective. Um, gotta think of like like you want to be like confident in your perspective. So knowing multiple perspectives makes you more confident because you know there's different ways and you know that one way might be more supported by evidence, for example. Um, so yeah, we start by writing coordinate systems. So x of t, so x, y. So if you like kind of tilt your head to the sideways, then you can kind of see like how it would be in one dimension. Particle might fly here. That would be your x. And then the height of the particle might be your y of t. So, when you draw draw a coordinate system. You could label it x, y, but really this y is the same thing as y of t, or I'm sorry, y of x in this case. So if you notice, one thing that's different is it's not t x. It's not t y z. It's x y z. So really, the function is vector function. It's kind of like x y z with a fourth time dimension. They're writing this compactly. They're writing this as r of t. It's a vector. So it's different ways of writing it, and it seems to be like, you know, they've been doing this for hundreds of years. This textbook is, in some ways, the condensed version of best practices. So there's merits to do what the book teaches, and then there's also merits to do what you find personally intuitive. So at the end of the day, it's just critical thinking. It's just trusting your intuition. If it doesn't make sense to you, that probably doesn't make sense to someone else either. So okay, so particle at time t. Particle at time t. So this is a compact way of saying we have a particle at point 1. Your x position is x t1, y t1. Okay. Actually, we're gonna have to get more compact than this. So r of t1 is saying you have a unit vector matrix times vector x t1 y t1 c t1. Okay, and if you know matrix algebra, so this matrix is a n by n, and this vectors are vectors are matrices, but not all matrices are vectors. So it's really multiplying two matrices. The matrices have to follow an order of algebra. So this is an n by 1 matrix, or this is just a column vector. N rows. Okay, so this is a 3 by 1. So that means this has to be n equals 3. And if you know U3 is 1 0 0 0 1 0 0 0 1, where this is your I hat, this is your J hat, this is your K hat. So when you're multiplying two matrices, you need the inside to match. And I will verify it for you. What are the dimension rows of multiplying two matrices? The number of columns is equal to the number of rows. Okay. AV will be a column vector n by 1 rows. Okay, so A is n by n. Okay, so you see how the inside terms have to match. So the columns of U of n. So columns is this. There's 3 columns, 3 rows, 3 columns. That has to match the rows of this. Otherwise, vector multiplication just doesn't work. Okay, so how do you do that? Writing these variables as shorthand of this. So you're going to take 1 times x, 0 times y. So it's going to be 1 times x. I hope I'm doing this right. 1 times x plus 0 times y plus 0. Okay, so this is going to be it's going to be here. So it's going to be x t1 you're going to get y t2 y t1 z t1. So you might be thinking, why do we just start with that? Because if we just assume that this has a direction implicit, it's hard to break it apart. When we have a unit vector matrix, it makes it easier to break it apart, I think. But you know, of course, I might be wrong, so it's up to you to decide if that makes sense or not. So delta R is RT2 minus RT1. Okay. So 2 vectors coming from the origin. So one thing I struggle with is getting the arrow right. Now it's kind of counterintuitive to me. Like you take P2, you take this, minus this, and the direction is here. Why would it be here? I know that probably is just building off what you learned in basic vector algebra, but it hasn't really sunk in yet. So when we do practice problems, watch out. That might be one thing I mess up, is getting the direction right for displacement. Okay, so polar orbiting satellites. Satellite is a circular polar orbit. So we have the Earth. We have an orbit. Okay. Altitude. Okay, so we're gonna say our radius is 400 kilometers. Just gotta think. Yeah, so this is just radius. It's in the center. And this is... Okay. So we want to know the magnitude. So we want to know R and R's direction. When it is -45. So when the satellite is here, when, like, what's the magnitude of this vector? And what's the direction? Kind of a lot to this. So we like picture shows surface of Earth. So I think they make their own picture. We graph in 2 dimensions. Okay, so we get the known. So the radius of Earth is 637. So the radius of the satellite is 637 plus 4. Okay, so delta R is R of T2 minus R of T1. So saying this is RT2, this is R, so we're gonna find that. So I mean that's a way better picture than I could have drawn. I'll zoom in for you. Okay. 2 vectors. Okay. Unit vectors. Okay, so hopefully you guys did not forget how to rewrite these. So J, it's going up. R T2. Okay, so RT2. 670. Okay, so we are going to use our calculator we made a long time ago. Let me write these down though. 6770 times 6770. All right, so last time, it's been a while since we were using vector, but okay, so calculate the components, give an angle and a magnitude. So magnitude is 6770, our angle is -45. So I'm getting 4787 J plus or is it -I? See what the okay, so it is J. Okay, so you might be wondering how are we finding this? So we have this vector. It's at this angle. Okay. Now we know the radius r is the magnitude. We know this angle theta. So with this, should be able to calculate everything else. So what we really want to know is components. So we know r. We want to find the hypotenuse. No, we want to find opposite. So opposite. Okay, so we're going to do, or what we did. I know the calculator made it easy, but so TOA so that's tangent theta is over adjacent, which is our r. So we're taking the tangent of -45 times pi over 180, or 180 over pi. I think it's pi 1 over 180. But we're converting 45 degrees into radians so we can take the tangent of it. And then that is going to be our opposite over radius. Obviously, we're going to move the r over here. So it's going to be r times tangent -45 by 180 equals opposite. Okay. So here, if you want to know why, like where's the I hat, if you want us to spell it out for you, it's going to be I hat plus 0 I hat. Remember, I is the x axis. So if you're going 0 in the x direction, you're going nowhere. So R1 is just going straight up 670. So we want to know what this is. So we're getting 478. So what is this saying? Obviously, if you can see, if you went 677, so you might wonder why is this 4787, not 6770. So try to spell it out for you. We're finding this point. Radius is this, but you have to think it's a curve. So if you just dropped down, you're missing distance. It's not that easy. If you look on this graph, if you drop this vertical straight down, if you're following my mouse pointer, if you're dropping down 6770, you're missing a lot. So that's why it's a little different. So that's why the angle is important to know. Okay, so now we can find the displacement. So we're taking, so not looking at the textbook yet. Displacement of R is so 4787 minus 6770 I plus 4787 minus 0 J. And I think I wrote this wrong. Remember, this is J. These are actually swapped. So really this should be plus 0, and this should be minus 6770. So we should get 4787 I plus, it's going to be a negative number, so it's going to be negative J, some number times negative J. Remember, you can freely pull out the negative signs. It's just a matter of making it easy. Okay. So then magnitude of the displacement. So I know some textbooks, they use this as, they write it as the norm. So that's going to be square root of that. I'm just going to write in I hat something squared is 12,509. So that's just Pythagoras theorem, or the dot, or the whatever. All right, 10 minutes left. Good progress so far. So I know that like the hard part is going to be figuring out which X, Y, Z, like which of the two directions you're going to be taking the algebra of. I know that might be the hard part. So they're finding the displacement. So our final answer is going to be an arrow. Should say this is vertical. So our final answer is going to be an arrow going from here. But it should be, so I'm not sure why they want to plot this. Doesn't make -67 doesn't make sense if I graph it that way. So all right. Plotting the displacement information meeting here. When plotting, okay. So I think it's saying okay, so the satellite that was up here, to get here, it had to go this much east and then this much south. And the total distance is 12,000 kilometers. Like if you're gonna like beeline it there, that's how much you would go. If you're gonna take, I know, the component paths should be so. Um, Again, you can do Pythagoras theorem here. 12k squared equals 5k squared plus 11k squared. Um, so displacement vector gives the shortest path between 2 points in 1, 2, or 3 dimensions. So that's pretty neat. Um, it, it, uh, I don't know, like, it seems like a pretty two-dimensional problem to me. I mean, we only use I and J hats, so feels like this section is just kind of a reminder, just kind of a review of vector and one dimension motion. But I think this is a really cool fact. Shortest path. I'm a big fan of like optimizing. So uh, the total displacement is the sum of individual displacements. Brownian motion. So this is an important concept. If you know anything about Norbert Wiener. Norbert Wiener. Um, he pioneered cybernetics, and Einstein. They both worked on Brownian motion. So the mathematics for Brownian motion can basically be applied to, let's say you have a, a turret that fires at an airplane, and you have a human operator, and they're looking through a sight glass. So let's say the sight glass, it's got like, anyways, Brownian motion, I know the statistics of it can be used to adjust the aim. Like during World War II, they used grounding motion to make like auto aim. Think of like Call of Duty, like people that cheat with auto aim. Basically, that's what these guys did. Not necessarily Einstein, but Norbert Weiner. I read it like one of his books, and it was talking about how he basically he was working on a problem, and they realized this could be really good for a weapon system, and they basically classified his uh, research. So, Brownian motion is a chaotic motion of particles randomly suspended in a fluid. So basically thermodynamics. So three-dimensional. So we have particles inside of this container of fluid. Okay. So they're moving. So each particle. So P1. So for all P n square. For all P n square, there is a vector function R of n. There's a vector function. There exists. So there exists a vector. For all particles in the square, there exists a vector function. Okay, so displacement in numerical order of particle. So we're gonna focus on one particle. One particle displacement. Okay. R1, so we're just summing these, so 1, 5, 2i delta R of n is 2i 4, 2, 3, 5, 3, no, 1, -1, 0, 0j 3, 6, 7, 8, 9. 9k. Okay. Two I 0. This should be a J. This is 9k. Okay, so then you take the norm of delta Rn is 2 squared plus 9 squared. So you have to think I, so you're going this, and then you're going, okay, so K, this is your Z, this is your X. So you're going, okay, we're out of time. You're going this, and you're going up high, this. Okay, so to find the angle of this, you are taking opposite over adjacent. So we know this is 9. Yeah. Basically, it would be tangent theta equals 9/2. Because TOA 9 is, so 9 is opposite, 2 is your adjacent. It's hard for me to draw on this graph, so I apologize. That's not very clear. Okay. And respect to the XYZ plane. So I haven't done any like AutoCAD or FreeCAD, but in those programs you can actually take a 3D object and just view it from one plane. So that might be a tool you might be interested in. All right, so next video we'll get into velocity vector, which is pretty cool. Thanks for hanging out, and I'll see you next time.